a Vesper sketch for that. So SF4 was a trigonal bipyramid with one lone pair in the center. All right, is that symmetrical or asymmetrical? Is that an app or a NS? Right. If I cut it like this way, I kind of get 2 foreigns on this side and none on that side. Right. So this is going to be asymmetrical. Right. It's going to be an app. And because of that, it's going to be polar. Okay, so asymmetrical. Which way does the dipole moment point towards? To your left, to your right, up and down? Yeah, some of you are to the left, right? All right, so that would be the dipole moment, the net dipole moment for sulfur trichloride. All right, that's basically taking one of my equatorial position atoms off, and I have this situation here. Dipole moment pointing that way. All right. So if Beyonce and Jay-Z were here, Beyonce would say, to the left, and Jay-Z would say, no, babe. To the right, to the right. It doesn't matter. You can rotate the molecule, and that might rotate the direction of the arrow, right? But okay, yeah. So I'm gonna roll through it. I got some music going through my veins. I3 minus, last one. Is that symmetrical or asymmetrical? Okay, so I minus we determined was it was that, right? This is definitely symmetrical, right? It's linear. I cut it this way, cut it that way. Okay, it's very symmetrical. So this is polar or non-polar? This is non-polar, right? It's very symmetrical. It's not an app. It is the other option. All right. So, so this is non-polar because it is very symmetrical. Question, is this molecule polar or non-polar? If I cut the molecule in half here, do I get 2 equal halves? I don't, it's polar. Right? Now, when we get to chapter 11, I'll redefine polarity again for really big molecules. Okay, but for now, just look at the symmetry, and you can tell it's polar or not. Okay, here we go. Which compound is more polar? So between these two, So in this one, you've got two inner atoms, it's two carbon atoms. And to the one carbon atom on the left, you've got 3 hydrogens. On the other carbon atom on the right, you've got 3 chlorines. Right? In this situation, you've got a chlorine on this side, but you still have 2 chlorines on this side. So between these two, which one would be more polar? The one on the left, right? Because the chlorines have the collective higher electronegativity. All right, when they're on one side of the molecule, that means all the electrons are more on one side of the molecule. Okay, so if I replace kind of bringing up with bonds here, right? We store our bonds with electrons. Alright, so here's the molecule on the left. Here's this guy. Oops. Alright, so yeah, you got this chlorine here, but these chlorines are pulling more. You know, 2 big chlorines here are stronger than this one chlorine here. However, if I replace this chlorine and put it over here, and replace it that way, okay, now I'm on the molecule on the right. Clearly, this one has more asymmetry. All these chlorines now are just overwhelming these hydrogens. All right, and these hydrogens just getting left out in the cold. No electrons for you. Like in Seinfeld. No soup for you. No electrons for you.
So you're saying that because the one on the left has the chlorines all in a cluster.
Right, all in a cluster.
Makes it more, okay.
Right. It makes it more asymmetrical and hence more polar. Which way does the dipole moment point towards? Straight out this bond axis right here. Lots of electrons free left. Okay. What about if I compare this molecule, but then I replaced the chlorine with bromine atoms? All right, which one would be more polar? Are bromines more electronegative or less electronegative than chlorine? Yeah, chlorine's more electronegative. So which one's going to be more polar? The one with the chlorine or the one with the bromine in it? The one with the chlorine, right? That's going to be more polar. Right, so the extent of electronegativity affects polarity too. Okay, real quick, I'll leave off on this note. There's a concept called like dissolves like, and I think you've heard this before in Chem 107. But when you have polar molecules dissolve with other polar molecules, they mix. All right, that's called miscible or miscible. And if they are non-polar, coming in contact with polar, then they don't mix. So polars like other polars, non-polars like other polars. And as a result, sometimes you'll see two liquids mixed together, and you'll get layers. Okay, so, and this is due to polarity. Okay, so if you understand polarity, you know, will this compound dissolve in water? Well, it's got a pretty nice dipole moment coming this way, so it's going to probably mix with water pretty well because it's fairly polar. But if I took this off and just replaced it with a hydrogen, all right, here's a very non-polar molecule. Is this going to be very soluble in water? It's not, right? It's going to end up wanting to escape from the water. Okay. So, like dissolves like affects those things. Okay, so we'll stop here. Maybe upstairs I want to show you this stuff real quick. Okay.